Bismillah ar-Rahman ar-Rahim. Our second lecture in the chapter 6 of frequency domain analysis is related about the correlation between the frequency domain analysis and design and the time domain analysis and design. In the previous lecture, I have mentioned a group of advantages of frequency domain analysis and design over the time domain analysis and design. And if we go back to the first pages, okay, here in this page, I mention in the third point that there is a correlation between the frequency domain and time domain analysis and design, and we can predict the time domain properties from the frequency domain characteristics. So this is what we will show in the current lecture. This is what we will show in the current lecture. Okay. In this lecture, we will discuss this correlation. So the first correlation point is that the speed of response in time domain, which is related inversely proportional to the rise time. Okay, so if we want to measure the speed of the response due to step input, which is inversely proportional to the rise time. The smaller the rise time, the faster the speed of response. Okay, so the speed of the response is inversely proportional to the rise time. The smaller the rise time, the faster the response. So what does this rule says? The speed of response, okay, or 1 over TR is roughly proportional to the bandwidth. Okay, and in order to validate this rule, this is very important rule. This is very important rule that specify the correlation between the time domain and frequency domain analysis. So in order to explain this principle, we will take two closed loop systems of first order, and after a few minutes we will cover another two closed loop transfer functions or control systems of second order. So in the first stage we will take those two closed loop transfer functions, and both of them, they are of the first order. The first transfer function M1, which is a closed loop transfer function M1, is first order. As we see, it has a single pole at s is equal to -1, and this is the transfer function in the S domain. If we want to transfer it to the steady state frequency domain, then we will replace S by j omega, and we will get the magnitude relationship as given in equation 6.90. And we have another transfer function, M2, closed loop transfer function, which has a pole at S is equal to -0.2. So it's also stable. But if we will compare both of them, the first one, its pole is at S is equal to -1, while the second first order system it has a pole at -0.2. So this second one, its pole is closer to the j omega axis, while the first one is farther to the left in the j omega axis. And what do we mean? Let me explain it on this page. So we have two first order systems. okay, one which has a pole at minus 0.2, and this another one, it has a pole at minus 1. So this pole is closer to j omega axis than this pole. So this pole is closer to j omega axis than this pole. And if we will expect the response, this will be related to e to the power minus 0.2t, while this will be related to e to the power minus t. So this response is faster than this response, and we know that the closer to the j omega axis, the slower the response. The farther from the j omega axis, the faster the response, due to the exponent value. So this will be faster than this, or this will be slower than this. It's the same concept. So let's go back to our original page. So we have two first order systems, and the closed loop transfer function is given. So we have M1 and M2. Now we will assume a unity feedback closed loop control system, and if we have a unity feedback, the closed loop transfer function will be g over 1 plus g, and h will be unity. So through this process, we want to derive the formula for g. What does it equal? As a function of m. G as a function of m. So we want to derive the value of g based on the m value in order to determine the plant transfer function for both systems of closed loop as given in equation 6.19 and 20. So finally, we will reach to this relationship according to equation 6.21, that g is equal to m over 1 minus m. And for the first system, finally, g1 will be 1 over s. While for the second system, g2 will be 1 over 5s. Okay, and regarding the steady state error analysis due to ramp input, we are speaking about, since the system type is 1, the plant here is system type 1, and the plant here is system type 1. Okay, so we will estimate the error due to ramp input. Okay, because the error due in this plant and in this plant to step function, steady state error, will be 0. So the first non-zero, as we have taken in chapter of steady state error analysis, the first non-zero value will be due to ramp input. So we will calculate KV1, which will be 1, KV2, which will be 0.2. And finally, we will calculate ESS1 and ESS2. So ESS1, the steady state error, is 1, while the steady state error in system 2 is 5. So we expect that this has the system 1 has a smaller steady state error than system 2. So ESS1 is less than ESS2. So system 1 has smaller steady state error than system 2. And this is obvious from this figure. Here, this is the response of both systems, Y1 and Y2, due to ramp input. So it's obvious that Y1 is closer to the input than Y2. So this, I wish that everything is clear in this regard. So we will go to our main point. Our main point, we want to see the frequency response and the time response. And we want to see, is there any correlation between the bandwidth from one side and the rise time or the speed of the response from the other side? So if we pay attention to both figures, those two figures. Okay, those two figures, they represent the value, the magnitude of the closed loop transfer function in logarithmic scale. Okay, for both M1 and M2. So M1 is this response in frequency domain, and M2 is this. And if you remember, when we say the bandwidth, we define the bandwidth as the frequency at which the gain will drop to 0.707 or minus 3 dB. So here we have this minus 3 dB line, and we take it horizontal, and its intersection with M1 and M2 will be the bandwidth. Okay, so it's obvious that the bandwidth of system 1 is larger than the bandwidth of system 2. Okay, so bandwidth of 1 is larger than bandwidth of system 2. Okay, this is regarding the bandwidth. Now let us focus on this graph, which is related to the response. So Y1, this is the response due to first transfer function, and this is M1 and this is the M2. So as I said, Y1 will have in its time response e to the power minus t, while Y2 it will have e to the power minus 0.2t, and based on that Y1 will be faster than Y2, and this is related to the rise time here in this area or in this area. Okay, Y1, so it's obvious from this figure that Y1 is faster than Y2. So we have now to reach the conclusion. So Y1, speed of system 1, it has faster response than speed of system 2, faster. And M1 bandwidth, okay, is larger than the bandwidth of system 2. So the larger the bandwidth, the faster the response. This is what we claim in the previous page. So what did we claim in the previous page? If we go back, this is our claim. Our claim is the speed of response. Here, the speed of response is proportional to the bandwidth. The larger the bandwidth, the faster the response. Okay, so we have proved for this first order system that the system 1, it has a faster speed than system 2. This system 1, it has a faster speed than system 2, and from this figure we concluded that the bandwidth of system 1 is larger than the bandwidth of system 2. And finally we will correlate. We have correlated the relationship that the larger the bandwidth for this one, the faster the response for this one. So Y1, it has larger bandwidth, it has faster response, while system 2, it has smaller bandwidth and it has a slower speed. So this is regarding the first system that we have selected, the two first order systems. Now, here we will continue and we will take two second order systems. Okay, and their closed loop transfer function, M3 and M4. And this is the transfer function of M3 and this is the transfer function of M4. Here, both systems, they have zeta constant for both of them. Zeta is equal to 0.5. So, for system 1 and system 2, both of them, they have zeta is equal to 0.5. So, what's the difference between the two systems? The two systems differs in the natural frequency. So, for system 1, it's 10. For system 2, it's 30. Or for 3 and 4, what we mean here. This system and this system. So, and it's obvious here, for natural frequency, for M3 and M4, this 10 and this is 30. While zeta is the same. So, we expect that the overshoot is the same, while The difference will be in time-related parameters, because we know that overshoot is a function of zeta, and since zeta is constant for both of them, the overshoot will be the same, while the only difference between both systems will be the time parameters. So if we focus on those two figures, this is the logarithmic value of the magnitude of both of them. Here we have M4 and here we have the M3. And as I said, here is the minus 3 dB line for bandwidth, and this intersection will give us the bandwidth of M3, and this intersection will give us the bandwidth of M4. So this is the bandwidth of M3 and this is the bandwidth of M4. So which has larger bandwidth? M4, the bandwidth of M4 is larger than the bandwidth of M3. So bandwidth of 4 is larger than bandwidth of 3. So let us go to the time parameters. Time parameters, it's obvious that system 4 is faster in response than system 3. So the speed of system 4 is larger than the speed of system 3. And if we correlate this fact with this fact, it's obvious that the larger the bandwidth, the faster the response. The smaller the bandwidth, the slower the response. Okay, and as I mentioned before a few seconds, both systems, this system and this system, they have the same overshoot. Why? Because zeta for both of them is 0.5. So the overshoot is fixed while the time-related parameter is different. And in this case, Y4, or the response of fourth system, is faster than the response of system 3. This is why, because the bandwidth of system 4 is larger than the bandwidth of system 3. I wish that everything is clear in this regard. And this page also clarify our previous facts, that we have this closed loop transfer function. This is the input, this is the output, and this is the closed loop transfer function for second order system. Okay, and here is the frequency response of the second order system, and here is the time response of underdamped second order system. And this is the formula for bandwidth, and this is the formula for the rise time. So we have taken in the previous lecture, and here also in this equation, we know that bandwidth is directly proportional to omega n. While from the previous figures which we discussed in the previous lecture, bandwidth is inversely proportional to zeta. Okay, we have discussed this point in one of the figures in the previous lecture. Okay, if we switch to the time domain parameters, as omega n get larger, TR will be smaller. Okay, because all time related parameters, they are inversely proportional to omega n. The larger omega n, the value will be of TR will be smaller, and this means that the system will be faster. And its correlation with zeta, as zeta gets larger, then TR gets larger, so it's directly proportional. So what's the end results? The end results are here, that bandwidth and rise time, they are inversely proportional. Increasing omega n will increase the bandwidth while it will decrease the rise time, and increasing zeta will decrease the bandwidth and will increase the rise time. So this is the final conclusion, that bandwidth and rise time, they are inversely proportional. So this is from bandwidth and rise time. So what about the bandwidth relationship with the speed? They are directly proportional, because speed is proportional to 1 over TR, as I discussed in the previous page. Speed is proportional to 1 over TR. So this is the final results. That what is the final result? The larger the bandwidth, the smaller the rise time, the faster the response. And the smaller the bandwidth, the larger the rise time, the slower the response. So these are the final results as I discussed in the previous rule. So let's conclude the previous section and go to the most important section in this chapter, which is about the body plot diagrams. So in body plot diagrams, we will assume that we have a minimum phase loop transfer function. Minimum phase loop transfer function. This MPTS is minimum phase transfer function. But we are speaking about the loop transfer function, not the closed loop transfer function. Loop means it's GH. Loop transfer function is GH. Okay, so we are speaking about minimum phase loop transfer function. What does we mean? What does this mean that we have a minimum phase? What does minimum phase mean? Minimum phase means that all of the zeros or roots of the numerator and denominator polynomials, they are in the left hand side of S-plane. Minimum phase transfer function means that all of the roots of the numerator polynomial and the denominator polynomial, they are in the left half side of S-plane. So this is the numerator polynomial. This is the denominator polynomial. So all of the roots of the numerator and the denominator, they are in the left. Okay, so this form is given in the polynomial format, loop transfer function, L, which is equal to GH. It's given in the polynomial format. If we rewrite it in the factored format, so we will have M zeros, and we will have in general n poles, okay, for the loop transfer function. As we said, n is always greater than or equal to m. So the denominator polynomial order is always greater than or equal than the numerator polynomial. So what do we mean by minimum phase? Minimum phase, again, means that all of those z's, z1 till zm, and all of those p's, including the second order quadratic term, all of the roots of those two polynomials, they are in the left half side of S-plane. None of them is on the right. So this is the main limitation or the main condition of this body plot diagram, that we assume a minimum phase loop transfer function L, which is equal to G. So numerator polynomial and denominator polynomial. What else do we have? So we have again K, and we have a term that is new in our material. It's this term, the last one. It's the delay, e to the power minus TDS. E to the power minus TDS. This is the delay. This is the delay term, e to the power minus ds TDS. This is the delay term. This term, we did not deal with this term before. When we take root locus technique, this was not covered. Okay, but in body plot, one of the advantages of the body plot design and the frequency domain design is that it deals with delay, while in root locus or in time frequency, in time domain, we did not cover this point. So again, this is the factored form of L, which is equal to G of H, GH, and again the delay is there and K is there. Okay, and M is the numerator polynomial degree and N is the denominator polynomial degree. Okay, and we want to express this polynomial, okay, after writing it in the factored form, into what we call it collected gain format. Collected gain format. What does collected gain format? It means that we should take out Z1 from here, Z2 from here, Zm from here. We should take it out as a common factor. P1 from the denominator, P2 till omega n squared, we should take it out. So if we take all of these out, we will get in the numerator terms each term consists of 1 plus something multiplied by s, and these something that I have described, it's tz1, tz2 till tzm. And in the denominator, same thing. For real roots, we will have 1 plus something multiplied by s, and this something is the tp, tp1, tp2 till the last term. And for the quadratic term, it will be 1 plus something s plus something by s squared, and the delay is the same. So why we use this collected gain format? Collected gain format will facilitate or will make it easy, يعني بسويها أسهل for the calculation of the steady state gain. So if you remember KV, KP, KA in the chapter of steady state, we take the limit as s approaches 0. Okay, so in this case, if we substitute it, it will be, if we replace s by 0, so the first term will be 1. This will be cancelled. This will be cancelled. This will be cancelled because s is 0. This will be cancelled. This will be cancelled. And this will be cancelled. And this will be cancelled. So it will be k1 multiplied by 1, 1, 1, 1 divided by 1, 1, 1, 1 after calculating the proper system type. Take into consideration the system type. So here in the equation, in this equation, we have here k, while in this equation, we have here k1. What's the difference between k1 and k? This is the formula. K1 will be equal to original k multiplied by the factors that we have taken, z1 till zm, divided by p1, p2 till omega n squared that I have discussed. We are taking them out. And the values of tz's, they are 1 over z. And the values for tp's, they are 1 over p in this equation. So, if we continue our process, as we said, when we want to cover the frequency domain, we will replace s by j omega. We will replace s by j omega. So, the previous equation, we will replace each s by j omega, and we will get this equation. So, from the previous equation, which is the previous equation, this is the previous equation. We replace each s by j omega, and this is what we understood from the previous lecture, that we replace s by j omega. Okay, so if we replace s by j omega, okay, we will get this equation, which is equation 6.24. Okay, so we replace each s by j omega, and as I discussed in the previous lecture, we will rewrite this equation as magnitude and phase. Okay, we will write it as magnitude and phase. So if we write it in the magnitude case, in the normal magnitude case, not the logarithmic scale, if we write this equation in the normal magnitude case, of L of j omega, it will be the magnitude of K1. It will be the magnitude of K1 multiplied by the magnitude of this one, multiplied by the magnitude of this one, till the magnitude of this one. And we divide it by the magnitude of this term, multiplied by the magnitude of this term, multiplied by the magnitude of this term, multiplied the magnitude of this one, the delay. So in this case, it's multiplicative. So if we add any term to this loop transfer function, we cannot use the previous values or the previous graph of L of j omega. We cannot utilize it. So when we want to convert this multiplication and division process into another term, which is the addition and subtraction. The addition and subtraction, if we add a controller, then we add the contribution of the controller to the previous case of the plant, and by this way our design will be easier. But if we keep this multiplicative term, it will be very difficult to check the contribution of the controller if we will add a controller to the transfer function, the plant. So this is why when we calculate the magnitude of the transfer function, we did not calculate it in the normal scale. We calculate it when we take the magnitude, we did not calculate the magnitude in the normal scale. We calculate it in the dB scale, which is logarithmic scale, 20 log all of the terms. So it will be 20 log all of the terms, which is 20 log the first term plus 20 log the second, till we finish the last term of the numerator, this one, the delay. Then we go back down to the denominator. In the denominator, it will be minus term, minus till we finish. So we convert through this logarithmic scale, we convert the multiplication process here to an addition and subtraction process in this scale. And this is very helpful in the design process where we add a controller to the plant. So what do I mean by this? This is beneficiary in the design stage. Assume that we have an original plant, GP. Okay, and this is R and this is Y. And this response in time or frequency domain, it was not okay. So what we will do, we will add a controller to the plant. And this is Y and this will be the R. So when we add the controller, as we discussed in the time domain root locus, the controller it contains poles and it will contain also zeros, poles and zeros, this controller. So if we know the magnitude of the plant in the normal scale, when we add the controller, it will be multiplication. It will be a multiplication of the new poles and zeros of the controller by the existing poles and zeros of the plant. And in this way, we should redraw or recalculate the new transfer function, the magnitude of G, which is equal to magnitude of GC multiplied by the magnitude of GP. We should recalculate it from scratch. We will not make benefit of any previous information about this GP. Okay, if we have this GP, we know the graph, it's a graph, magnitude graph like this. Okay, so if it is multiplicative term, we cannot take any benefit of the existing graph of GP. While if we convert it to the logarithmic scale, we make then U we make the new magnitude of G is equal to the new magnitude of GC in dB plus the magnitude that we know about the plant also in dP. So if we have this term or this graph, then we can add the contribution of the controller graph to this graph and we can utilize the information that we have. And this is why we did not use the multiplication scale in the normal magnitude, and we convert this from the multiplicative form to the additive form. So again, this is additive form for the additive and subtractive form for the magnitude. And when we say about the phase is already additive for the numerator terms and subtractive for the denominator terms. So we don't have any problem with the magnitude, with the phase, but our original problem was in the magnitude, and we have solved it by using the logarithmic scale in order to convert multiplication into addition and division into subtraction. So if we pay attention to our transfer function that we discussed, this transfer function, if we pay attention, okay, it consists generally of 5 forms or 5 basic factors. So we have basic factors for the transfer function. Okay, for any arbitrary loop transfer function, they are: number 1 is the gain, K. Number 2 is the system type, or if there are any zeros, so they are integral or derivative. They means that they are poles or zeros at the origin. This is the second term. The third term is real poles or zeros of multiplicity Q. The fourth term is the complex conjugate roots, and the fifth term is the pure delay. So these are the most comprehensive terms that we can find in any arbitrary transfer function, loop transfer function. Again, what are they? They are the constant gain K, and they are poles or zeros at origin. They are real poles or zeros with multiplicity Q, while the poles and zeros at origin, we assume their multiplicity is n. For real poles or zeros, multiplicity is Q. And the fourth term is complex conjugate roots, and the fifth term is the pure delay. So these are the 5 basic factors in the previous transfer function that we discussed till now. Gain, or poles or zeros at origin, or real poles and zeros, or complex conjugate roots, poles or zeros, or pure delay. And the second and third term, they might be simple or they might be repeated. Okay, so since we convert the magnitude into summation and subtraction, and the phase is already as shown in equation 6.26, it's already in the summation and subtraction form. So if we know the contribution of each phase, of each basic factor, of those 5 basic factors, if we know how to draw those 5 basic factors, okay, then it will be easy for us to construct the overall diagram of the root locus of any loop transfer function L, which is equal to GH. So if we know to draw each of the 5 basic factors, their body plot or frequency response or frequency plot, then we can add those or subtract them depending on whether they are in the numerator or in the denominator. In the numerator we add, in the denominator we subtract. So if we know how to draw each of the 5 basic factors, those 5 basic factors, then we can construct the Bode plot of any general loop transfer function L of GH, and this is written in this phrase. So at this stage I will finish this lecture, and our next lecture will be about how to draw the Bode plot for each of the 5 basic factors. Thank you and see you soon.